Got it. Hello. Not sure how long until, it's not really yet. Setting up your meeting for streaming service. It might already be live. I'm not sure. It says it's setting up. Cool. Hello. Welcome to Cosmology from Home, AMA 2023. We're all cosmologists at a academic cosmology conference online, and we're here to answer your questions about cosmology. I think the first question we were planning on answering, Nico, you want to remind me what that question is, and then we can all answer it one by one and introduce ourselves.
Not a problem. So this question is for everyone. How did you each get started working in cosmology, and are there any upcoming cosmology experiments that you're particularly excited about? So let's start with Sean.
Okay, I was going to start with you, Nico, but okay. So any experiments that I'm excited about? I guess just about every experiment is exciting. I don't know if there's any I'm particularly excited about. One that's exciting and it's kind of space age science fiction kind of stuff is this LISA gravitational wave experiment, where there'll be 3 separate detectors in space shining lasers at each other, working exactly like these LIGO and Virgo gravitational wave detectors that I think we'll get to at some point in this AMA anyway, but working exactly like that, but in space. And actually there's a hypothetical one in the future, even beyond that, called the Big Bang Observer, where you've got 3 LISAs all shining at each other, which is completely nuts, or something like that. So that's kind of exciting just because it's so weird. And how did I get interested in cosmology? I guess I just wanted to study and learn about the most fundamental stuff I could. And cosmology seemed more observationally vibrant than particle physics when I was a student. So next, let's go with Min.
Oh, hey, yeah. So, yeah, so I think I also started in cosmology just because I was curious about the universe and where we all come from. So regarding the experiments, the upcoming experiments, yeah, I think all of them are excited, but I'm most excited about the cross science between them. So, for example, between DESI, which is a galaxy survey, and, for example, SO Simon's Observatory, which is a CosmicMicrowave Background experiment, because by crossing these surveys, we can extract much more information from each of them individually.
Cool. Next on my screen would be Robert.
Yeah, hi. So I'm Robert. I started in cosmology pretty randomly because I just heard some nice lectures about it, and then I thought, oh, that's interesting, and I kind of got stuck and got excited about it when I studied my undergraduates in physics. Yeah, so I'm most excited, like a bit by nature, by the Euclid satellite, which was launched a few weeks ago, because I work a lot on gravitational lensing, especially the weak gravitational lensing part, and in current surveys, the kilodegree survey, for example. So that's why I'm excited about this, but it's in a very good time, because a lot of new data is coming in over the next decades in various experiments. And yeah, I will give the ball now to Jenny.
Hi,
I think Jenny froze.
I was 16. I was intrigued by gravity and this interaction, how it works. And at the moment, I'm very excited about the James Webb Space Telescope. It's been like a year since the first pictures, and the increasing amount of detail that we can see there is very interesting for me, because I also work on dark matter properties. And so I'm interested in, can we constrain the nature of dark matter, which is still a mysterious matter form in our universe? And I'm pretty sure that James Webb will shed some light into this darkness. And now I'd like to pass over to Pankaj.
Thanks, Jenny. So like most people here, I got interested in cosmology because I'm fascinated by the universe. Most of my initial learning was from popular science. My background is actually in computer science, and there came a stage where I realized that the popular sciences are just like not doing enough to satiate my curiosity. So I had the math knowledge. I just wanted to just learn more about it, and that's how I switched over to actually like studying cosmology in school. It's been very interesting. About my favorite experiment or survey, I'm pretty fascinated by dark energy right now. So any experiment that's going on related to dark energy is pretty exciting because we need a lot more data for dark energy. So Euclid has been launched, and then LSST and also the 30-meter telescope is in development. So we're pretty excited about that. And then I'll pass it on to Nico.
Hi, everyone. My name is Nico, and I work in Newcastle in the UK. I started getting interested in cosmology during my undergrad studies in, excuse me, in astrophysics. I just thought it was super cool that you can try to explain the universe as a whole instead of focusing on planets or something like that. The experiments I'm excited about, well, as everyone said, all of them are great, not just in astronomy and astrophysics, but also in particle physics and beyond. However, I have to give a special place to Rubin Observatory because I am part of that collaboration. So go LSST.
Cool. So we'll start working through some of the questions. We'll answer the questions. This is tied to a Reddit AMA, and we'll start answering some of the questions in the AMA. Those of you who are present in YouTube, don't be shy and feel free to ask questions yourself. And if you do, we'll answer them. They can jump the queue because you're here live. So for the first question, Min, do you want to have a go at answering how do scientists find the CMB? Can I point a telescope or the instrument used to locate and capture it just anywhere? If our universe has since expanded, how do we get the snapshot that is almost 14 billion years old? Wouldn't that light have expanded with us? And is it true that a part of older television snow was interfered by CMB?
Right. Thanks, Sean. Yes, so thank you, NFB Potus, for the question. Indeed, the CMB radiation comes from every direction. So regardless of the direction you point your telescope towards, you simply cannot miss it, right? And that said, of course, since the CMB radiation peaks within the microwave range of wavelengths or frequency, so your instrument must be able to capture or should be sensitive to this microwave radiation for you to be able to observe it. And then I think the second part of the question is that if the universe has since expanded, how do we get the snapshot of the universe at 14 billion years old? So that's also a very good question. So the CMB radiation of photons travel at the same finite speed, right? So at any given time, the CMB photons your instrument record all come from the same spherical surface relative to us. So this spherical surface is what often referred to as the snapshot. And because the universe expands, basically the time that it takes the photon to travel towards us is basically 14 billion years old. And that is the age of the universe, essentially, or the observable universe. I think there's the last part, which is, is the television snow is actually, so the television snow receives some contribution from this cosmic microwave background because it just comes from everywhere. Because the microwave is next to the radio wavelength, so parts of the CMB will leak into the radio wavelengths. But I think this is only true for all televisions.
Cool. Nico, do you have some things you wanted to add to that?
Yeah, just in general, when you have a theory in physics, then you basically build a model, which is an idealized version of reality that you think is true, or not reality, of a physical system that you think is true. And then you know what to expect there. So in terms of the CMB, you predict what kind of signal you're going to detect, should be able to detect, and then you build a machine or a device, which is a telescope or a detector that's going to detect exactly that signal, sensitive in that region. So this is how it works in principle.
Thanks, Nico. I guess one thing that I might add, which I find kind of interesting about this, is that there are kind of two places where CMB telescopes tend to get built: space and dry places. And one of the most interesting things I find about this is that one of the driest places on the planet is covered in ice, which there's lots of water around. It's just not wet water, it's frozen water, so Antarctica. And this is because the microwave background interacts a lot with water vapor, so you need a dry place. The other place is the Atacama Desert in Chile, which is apparently, apart from Antarctica, the driest place on the planet, and also at a high altitude, which means there's less atmosphere. So even if there is a little bit of water vapor, there's even less to go through. But it does mean that CMB science is often not so much shut down over the Southern Hemisphere winter, but slows down because there aren't people. Actually, there are some people still on the South Pole, but just not that many. And then over the summer, they will go down there and improve their telescopes. So the next question I think we have is for Jenny, and it's a very, very deep fundamental one. What do you think was happening before the Big Bang?
Okay, so I'm also interested in philosophy of science, and I think this question partly falls into that regime, because when we take a look at how our cosmological model came about, it more or less started by Georges Lemaitre thinking about creation of space and time. And so his idea of the Big Bang was that everything, including space and time, was created in the Big Bang. And this is our standard model we have today. But as Ming already said, our first observation, our first picture of the universe comes from a much later time. So actually, from the observational point of view, we cannot know whether the Big Bang actually happened and what is before the Big Bang. So everything that we do there is more or less theory-based, or even based on more like principles, philosophy, whatever you think could there be. As long as you kind of like are in accordance with the observations that we have, for instance, from the nucleosynthesis or from the cosmic microwave background, there are a lot of different theories. For instance, you could say, I believe Sir Roger Penrose, who put forward the conformal cyclic cosmology, and he has an idea like sugarcane-like cosmologies, where you have so-called eons, and each eon kind of like goes into a region which is more or less an equivalent to the Big Bang, which is like highly dense, and then it collapses and then it explodes again. And so we have like different kind of like cycles in compression, expansion, compression, and so on. And so this is, for instance, one potential theory. And for me personally, I would say, for me, everything stops at our observations. So whatever is beyond this is speculation, but I'm very happy to kind of like see all the theories and to explore what kind of argumentations there are in order to reason what could there be.
Cool. One thing I'd like to follow up on that, which is kind of completely off topic to the question and to Jenny, but just for anyone watching, be wary that cosmologists and scientists use the two words Big Bang in two different ways. One of them is this kind of very initial singularity when who knows what happened, which is kind of what Jenny's been answering, and I think was what the question was about. But then a lot of the time, maybe even more often, cosmologists are talking about the Big Bang, just meaning the kind of post that initial thing, hot expansion, where things like nuclei are formed, where things like the cosmic microwave background is formed. In fact, almost now is also sort of part of the Big Bang. It's just this big explosive expansion thing. So it can be confusing sometimes when cosmologists are saying, you know, we have all this evidence about the Big Bang. What they're meaning is evidence about the abundance of light elements and the cosmic microwave background. And they're meaning the second use of the word Big Bang, phrase Big Bang, but not the first one. Okay, so next one, do we want to have Robert answering, what if the baseline fundamental assumption of a homogeneous universe from the cosmological principle is incorrect?
Yeah, I mean, that's a tough question. So we actually had quite a few discussions, I think, during this 2-week conference here about this stuff. And so if it's incorrect, so if the data basically points in a direction where we have to abandon basically these symmetry assumptions, then we basically have to go back to the drawing board, right? So the main reason why we do these symmetry assumptions, because there's a theme in science, which is simplicity, right? So if two models fit the data equally well, you prefer the simpler model, so the model with less freedom. And but if there's at some point enough evidence that the simple model is incorrect, then you have to abandon it. But the issue is that writing down general solutions to our theory of gravity, which don't have these symmetries, it's really, really difficult. And calculations become much, much harder. And so for example, for a space-time or for a universe where you give up both of these assumptions, it is almost impossible to do it on paper, basically, and is also super hard from a numerical point of view. But if we find at some point that these things are not true, and we find it in the data, again, going also back to what was said in the question before by Jenny, is that, then we have to face this reality and go back and try to build a new model. But for all we know at the moment is that the current model we have fits very many observations very well. There are some discrepancies and some anomalies which are discussed in the community, and there are also models which, for example, give up homogeneity. These are the so-called Lemaitre-Tolman-Bondi models, and there are also models which test the anisotropy of certain observations, for example, of the CosmicMicrowave background. So we will have to wait basically for the new data. This is why it's also exciting, because then the data will tell us if these things are correct or not.
Cool. Jenny, I believe you'll want to weigh in some more on that, as this is an active part of your research.
Yes, exactly. So I'm one of the authors who wrote a recent paper on the anomalies and oddities that we find, which seem to kind of like be hints to abandon our standard cosmology. And the question now is this enough to abandon our standard cosmology? So can we prove the cosmological principle wrong or not? And here we found that it's quite interesting that we can actually still reason for two different viewpoints. We can say on the one hand, okay, our current cosmological concordance model requires some extensions. We cannot explain everything from the cosmological principle plus the physical contents that we have already observed. There must be something more. If we accept this and we say, yes, we extend it, for instance, some special dark energy or so, then we can keep our cosmological principle and our simple cosmology. On the other hand, there's another camp saying, no, I do not accept all of these extensions. And so I'm rather in favor of keeping my astrophysics as it is. We already have mysterious dark energy and so far undetected dark matter. So let's keep it like this. And let's make our cosmology a bit more complicated. As Robert already said, the calculations get far more intricate and we need more computing power for this. But in that sense, we can keep our astrophysics still simple. So these are the two kind of like camps we currently have. And we're waiting for the next data in order to kind of like see which argumentation has more arguments.
Awesome. Thanks, Jenny. The next question for you, Nico, you wanted to answer this was,
so
why can't
this? Oh, sorry, you're gonna read.
Oh, you can read it. Go ahead. Yep.
Yeah, sorry. Why can't the CMB be the combination of even farther, more distant galaxies and cosmic objects whose light has spent so much time drifting through space that it has redshifted to the point of being microwaves? So the answer is no, it can't be. We know specifically that it is the CMB. And why is that? So if you go back to the video at the beginning where I mentioned these models, right? So you construct a model that describes a certain thing. And there is such a model in, the idealized version that we assume is true. That model is called the black body. And black body tells you, describes how the radiation is going to be emitted from a body that is very hot and very dense. For example, stars are such bodies. They are very compact objects that will radiate, so you get photons, right? From the sun, you have the light. And then you go back in time. So if our theory or hypothesis that the universe started from something very small, as a very small, very dense object, then following up with that theory, that means that it should radiate as you're going to have emission of photons. So that means that you should be able to observe this black body spectrum. And this is the case, what we observed first with, first it was discovered by Penzias and Wilson back in 60s last century. And then they built a more modern version. It was called COBE, 1965. Yeah, thank you, Jenny. And then then you had a proper probe that was called COBE. Then we had WMAP, and then we have Planck, it's the latest one, satellite. So the difference between these devices is just the increase of resolution, like you have on your phone, right? Just a better resolution of, for example, the image. So in that sort of sense, it cannot be distant galaxies, because if you think about it, the way we probe different stuff in the universe, we build different, as I said, different detectors to do that. And one thing that we have in our, that we know really well in physics is how to do spectra, for example. So we would know if it's, if the light is coming from a galaxy, we can distinguish if it's from a star, if it's from actually different types of stars, if it's coming from a different, for example, from a black hole, and these sort of things, right? So that means actually black hole, I should say, active galactic nucleus. So the whole compact region in centers of some galaxies. So we know it can't be galaxies, it can't be stars, because we can distinguish those. And once another thing, it is coming from every part of the sky, everywhere in the same manner. So considering the theory and considering the observation, it is exactly, I should not 100%, but very, very likely that that is the case. Anybody wants to follow up? Because Minna, maybe you are better at CMB.
Yeah, I wanted to follow up. I think what Nico said is enough evidence that, yeah, it's super compelling that the CMB is indeed from, you know, this early universe epoch. When one just had the black body spectrum, it was still possible to speculate on less likely alternatives. So yes, the light from a star would be recognizable, but people were speculating still that maybe all of the light coming from distant galaxies, and this is like the concept of an infinite universe, is like scattering off dust. And as it scatters off dust, it loses its precise spectral nature, and it eventually kind of just equilibrates to a black body. So that there was a quite technical terms. It just keeps scattering, and instead of having particular colors and frequencies, it spreads out into this black body. And if you've got an infinite universe with an infinite amount of time for that to happen, maybe it can still look like a black body. But nowadays we have measured the tiny little fluctuations in the temperature of the cosmic microwave background at different locations in the sky. It's still a black body at each location, but the temperature is slightly different. And okay, that on its own is not all that interesting. But if you think about the two different stories, in one of them you have this infinite age universe with tiny little fluctuations in the temperature just based on tiny little differences. And in the other one, you have a finite age of the universe where these tiny little fluctuations only existed for a little amount of time. Now, if I have a universe and I put tiny little fluctuations in its temperature and density, what do you expect to happen? Well, the slightly more dense areas will accumulate more, the slightly less dense areas will move apart. But also, when you've got this early universe with ionized hydrogen around, so protons and electrons, you get sound waves. As you get an area that's too dense, it pushes back and it starts to expand. And so this hot plasma of protons and electrons should have sound waves traveling through it. So these tiny little differences in the temperature of the cosmic microwave background should look like they come from sound waves. And they do. So this is just overwhelming evidence that it was a Big Bang, that it was a rapid expansion, and that the cosmic microwave background comes from that and not from some other type of thermal equilibrium. And there's an even further step, that this temperature should then be polarized based on how it formed at this last scattering thing, and then it looks like the polarization as well, which gets quite technical, but it's yet another level of inference that is extremely subtle and is precisely how it's predicted. So yeah, what Nico told was kind of enough, but then there's two additional even bigger sledgehammers of no, it's actually coming from the early universe that one can add, that are both, you know, two levels of technical difficulty above it. So I think the next question you wanted to answer, Pankaj, which is hopefully we don't have anyone suffering existential dread in the audience, but if anyone understands the size of our blue marble in comparison to the universe, I presume it's you guys. Maybe, I don't know. You can do the numbers, but I'll let Pankaj answer. But does Earth's size in the universe cause you existential dread? If so, how do you deal with it?
Yeah. So first of all, great question, Fred D500. I would say you deal with it like you deal with any other thing that causes you existential arthritis. Like, you take in the emotions, but then you eventually look at the positives to go with it. In my personal opinion, just feel like to be able to understand how the universe works, to be able to be in a position to answer questions like, where we came from, what is the future of, the universe itself, using precise data from telescopes and surveys, and like getting an answer like through science, which has like, backed by data and evidence. There is a sense of like humbleness to it, and in my opinion, like almost like a sense of spirituality that can rival any religion, in my opinion. I don't know. Would you guys, anyone else wants to chime in?
Yep, I think both Nico and Jenny have said they want to follow up. So Nico first, then Jenny.
Yeah, just in a sense, yes, it gives you a perspective of how insignificant we are and how none of it matters. Like, not none. There are things that matter in life, but maybe don't sweat the small stuff. So maybe you get, at least I get that perspective. Like it's all fine, and just use your time in a very, I don't know, efficient way. Don't waste time on, I don't know, irrelevant things, because our time compared to universe is well, insignificant. So maybe just in that sort of sense, but nothing like existential. You just do your life normally. Jenny?
Yes, I mean, I agree to Nico. I would also say when we put this into a larger perspective, I think that we should become aware of that we are all in the same boat. We are all on the same blue planet. And so I think we as mankind should kind of like collaborate a bit more in order to push our own boundaries further. I mean, like climate change is one point, but I think also like space exploration, if we all work together, we can explore more and deeper into space, because if we all pool our forces, we will see more. And so I think for me, it's not an existential threat in that sense, but it's more like a possibility. And I think it's pretty cool to see like these exoplanet searches and to see, are we actually alone? I mean, it would be really great to find life on other planets and to see we are not special. There are other, I mean, entities out there which are also conscious, which are also living. I think this is something that I would rather like be keen on seeing.
Cool. I just have hopefully a quick comment. You might have noticed me kind of giggle when I was reading the question out when it was like, you guys should understand it. I guess in some ways, yes, maybe we can calculate the numbers and we see, okay, this number is 100 times bigger than this number, and this number is 10,000 times bigger than that number. But if you mean like truly like feel it and understand it, I'm not so sure. Like we evolved in the same caves that you evolved in. I can kind of understand. I live in Auckland. I can kind of understand the distance to Hamilton, because I think if I walked it, it would take 3 or 4 days. But I'm not even sure I fully grasp the distance between here and the United Kingdom or here and somewhere else. Like I get on an aeroplane, and it flies there, but I'm not sure. So these cosmological distances, it just, as soon as you get to the size of the solar system, it's already just blowing the brain. And so then when you get to galaxies and universes, it, on a kind of deep visceral level, I don't feel like I can properly grasp it. Okay, the next question. Robert wants to have a go at answering it. I've never understood how this background, I guess cosmic microwave background, can still be around. Since nothing travels faster than light, how is it that the microwave background hasn't already reached us? Does it get reflected off something and bounce around?
Okay, yeah, that's an excellent question, I think. So the main point is that, so we see the cosmic microwave background from when it was released, and it was released, well, for all practical purposes, roughly 14 billion years ago. And so we see it at this distance. So it took basically the cosmic microwave background of the radiation we see today, these 14 billion years to travel to us. So we basically see a point or a shell in space, which is these 14 billion light years away from us, right? So the cosmic microwave background, when the universe was younger, which was at our position now, basically is seen by an observer, which is basically at the position where we see now the cosmic microwave background, right? So every observer basically has a spherical shell, what we had at the very first question, a spherical shell around it where he sees it, because this is basically the distance light traveled during the age of the universe, or no, well, the time since the cosmic microwave background was released, which was 300,000 years after the Big Bang, or after time zero, when the universe basically started. And this is why there is a cosmic microwave background which we detect now, but these are not the photons which were released when it was released. Those are of course long gone, but it is not reflected.
Cool. Both Nico and Min want to follow up. So, yep, Nico, then Min.
I just wanted to add that why can we observe, maybe in the simplest terms, and please, CMB people, correct me if I'm mistaken. There's a lot of photons. This is, I think, there's also one of the main reasons why we can still detect them. There was a lot released at the time of the CMB. Somebody else can follow up?
Yep.
Yeah, and I think also, I mean, there may be one technical detail that I can point out is that the last scattering surface is actually not a surface, right? It's a layer. It's more like a layer. So you have photons from different redshift, different time coming towards us now and then. I just want to quickly follow up on the second part of the questions, is about whether these photons bounce off something. So they do bounce off. For example, free electrons in the universe, right? In galaxy clusters where you have a lot of like ionized gas, hot ionized gas, and then you have free electrons moving around. So when they bounce off these free electrons, they do exhibit some shifts in the CMB black body temperature, and then using these shifts, we can actually study the free electrons inside of these galaxy clusters, which to me is very cool.
Awesome. I think the next question we were going to go to was also for you, Min. So yeah, as you pointed out, it's a little bit technical, but we'll have a go. Any chance of observing B modes after the Bicep 2 fiasco, or is that out of the window?
Yeah.
So we just point out the Bicep 2 fiasco was the Reddit AMA's words, not us here. So yeah, Min, maybe give a bit of background, because obviously this person who's asking the question probably knows what those words mean, but the audience might not.
Yes, sure. And by the way, I don't know which order I should put the questions in the list. So I mean, because I usually put my questions in very late, but they got read out earlier. But yeah, anyway. So yeah, I think the question is concerned with the first of all, B mode's polarization refers to the polarization of the cosmic microwave background photons, and the polarization are usually decomposed into two modes, E mode and B mode. And the reason that B mode is interesting is because so B modes also have different contributions, but the most interesting contribution is coming from the primordial gravitational waves in the very early universe. And observing these would be very, I think it would be a smoking gun for inflation in particular. So that's why people are really interested in primordial B mode. And then the question is, after the problem with Bicep 2, do we still have hope to observe this? I think I would say, I wouldn't say a definite yes, but I would say that it's very optimistic for a few reasons. The first reason is that because Bicep 2 actually provided a very good characterization of the dust properties, which is the main contamination for this kind of observation. So even though it failed to observe the primordial B mode, we understand the dust very much better after Bicep 2. And then the second reason is that we are now going to have, I think, CBS4, CCAT, and then a Lightbird that going to focus or hammering on B mode, trying to extract this primordial B mode from the CMB. These experiments are special because they're going to observe the cosmic microwave background at many frequency bands. And this is important because if we have the CMB, if we observe the CMB at different frequency bands, we can characterize the dust again and other foregrounds very well. So we can have the hope to separate the primordial B mode from other contributions.
Thank you, Min. Okay, I think the next question, they're encouraging me to answer it, so I'll have a go. What is fuzzy dark matter rather than wave-like axions or particle-like WIMPs? So yeah, on the Reddit AMA, I guess I had in my keywords fuzzy dark matter. So to the person who asked this question, I have a very trivial, easy answer. It's not different to wave-like axions. It's just a different way of saying the same thing. So if you understand wave-like axions, you understand fuzzy dark matter. They're not different. It's also sometimes called ultralight dark matter. This is one of those things where different groups started calling it different things, and it hasn't converged on, no, this is the way we'll call it. So I don't know. I chose fuzzy dark matter. Someone else chose something else. For those who aren't the person who asked that question, who maybe want a bit more detail about what are wave-like axions and what are particle-like WIMPs, I'll have a bit of a go. So WIMP stands for weakly interacting massive particle. The weakly there historically initially meant the weak nuclear force. Now it kind of means either the weak nuclear force or just a weak force. But these massive particles tend to be at least approximately the mass of the proton or more massive. And it turns out that if you have about that mass and you are interacting weakly, as in about the strength of the weak nuclear force, there's a thing that is called the WIMP miracle, which is quite persuasive, which is that if you have that mass and you're interacting about that strength, then as you go through this hot Big Bang, the second definition of Big Bang I was using earlier, this radiation, lots of hot nuclei and particles floating around, you actually generate dark matter with approximately the right density to be the amount of dark matter we have now if it interacts weakly. So that's why WIMPs were super, super popular as a model or a framework to build models around. Unfortunately, if they're weakly interacting, as in the weak nuclear force, you should also generate them if you get to high enough energies that they're possible to generate. So the sort of things that would have been satisfied by the WIMP miracle should have been detected by now, apart from some obscure regions of parameter space. So it's still possible that there are WIMPs, but they're becoming less popular as their space gets ruled out. Another option are these wave-like axions. So you can get dark matter generated earlier in the universe's history. And again, you can kind of get the right abundance, like the right density of it. If it's very, 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 very light, so light, in fact, if you have basic quantum mechanics, you know that there's this wave-particle duality, that particles have a wave-like nature, and this wave-like nature is related to its mass and its speed, the de Broglie wavelength. If it's sufficiently light, it might even have like galactic or astronomical sized wavelengths. Like an electron has a tiny little wavelength, but a dark matter might have wavelengths that are sort of a quarter the size of the Milky Way or a tenth the size of the Milky Way. And then this becomes very interesting phenomenologically because it can't cluster more tightly than that. So you would, for example, you wouldn't see anything that's below some minimum mass threshold because it wouldn't be able to cluster unless it was more massive. You shouldn't see fine gravitational details, at least on a smaller distance scale than that, because it can't cluster. Obviously normal matter can cluster more than that, but most of the matter is dark matter. So it's very interesting in that sense. But yeah, it can have many different names. So the next question could be, it's difficult when I was the one answering the question. So who hasn't had a question for a while? Nico. Okay, I'm going to ask this question that has just jumped out to my eye. I have no idea where this is going, but we're just going to go with it. Could dark matter be fungus? I'm not sure what you mean by that question, but if the planet and everything on it was shrinking in relation to the rest of the universe, how would it look like from Earth? Okay, the second part of the sentence makes sense as a question that might be interesting to answer. The first one, you're welcome to have a go, Nico. Could dark matter be fungus?
No, it can't be, because the way we are detecting, as we elaborated several times during this live stream, we can actually not only infer what type of object the light is coming from, but also how far away it is. And well, secondly, well, some bacteria or fungi have certain properties like fluorescence, and well, I'm not a biologist, but I know for a fact that that's true. But it is absolutely not the case that we are detecting light or any kind of emission from fungi in space. This is it can't be from that. Another thing, what was yeah, Jenny, maybe you can follow up, please.
Yes, I mean, I'm not sure how the question was phrased, but sometimes fungi are supposed to be like self-organizing. And maybe there was an idea like, is dark matter kind of like a self-organizing structure? And so I did some research on like self-similar universes, like that we say we have gravity, which doesn't have a preferred scale. It acts the same on every scale. And this, as such, implies that we have a kind of self-similar structure growth. Some people call it fractals, but I mean, fractals are a mathematical term, and I prefer to say self-similar because it has like a lower scale and it has an upper scale where this kind of like self-similarity breaks. But you can say because gravity is acting the same everywhere and all of the time, you could see these dark matter structures which seem to be the same on all scales, like as a fungus in the sense that they are more or less self-organizing. But I wouldn't go as far that they are kind of like organizing themselves. I would say it's just based on the laws that we have. And these laws imply that it looks like we have a self-similar structure, but I wouldn't call this like self-organizing in that sense, like conscious directed motion.
Nico, you want to jump back in?
Yeah, just to conclude this, it is not coming from fungi. What Jenny was saying was talking about a property of fungi and a possible property of certain matter, but there is no correlation beside that. So what you asked, the simple answer is no, it's not coming from fungi. Okay, Pankaj, maybe you want to?
Yeah, let me just read the question out because, or do you want to read the question out, Pankaj, or?
Well, which one are you at?
Yeah, good point. Hold on. I just lost it for a second. Yeah, I have a question about the practical implications of dark matter. Let's pretend that you have two bowls in front of you. One bowl contains matter, one contains dark matter. The matter bowl noticeably contains stuff that you can visually see, physically feel, and it has a measurable weight when you put the bowl on a scale. What are the properties of the dark matter bowl? Does it just look empty? Can it be weighed? How will we ever know it has dark matter versus just being empty? I struggle to grasp how the large-scale concept of dark matter shrinks down to a more relatable scale.
Yeah, great question, Delta_Bell. So this has always been like, as someone who's interested in like science communication and related to astronomy, like explaining this on like in a way that makes sense to an audience for dark matter has always been hard. Coming to your questions, if you have this bowl of normal matter versus dark matter, does it look empty? Yes, it will look empty to your eyes because the dark matter does not interact with light. Can it be weighed? Yes, it can be weighed because it interacts gravitationally. In fact, that's the only way that dark matter is known to interact. How would we ever know it has dark matter versus just being empty? You can't know it this way because you can't take the dark matter particles out of the bowl because you can't see them, right? The only way to directly detect dark matter is to hunt, or the only known way to directly detect dark matter is to hunt for dark matter particles. And scientists at CERN and other particle colliders are working hard to do just that. One last thing that I would like to mention is that the reason that a lot of this, so there's one point which is like, a lot of people seem to think that, we have just the same amount of dark matter here as normal matter at the scale of solar system. That is not true. Like at the distance that we are from the Milky Way, from the center of the Milky Way, the dark matter density is about 1/100th of what the normal matter density is in the solar system.
Yeah, I might just follow up a little bit as well. Yeah, so I guess having a bowl of dark matter is in some sense not even possible because the whole point of dark matter is it doesn't interact with normal matter. So if you tried to contain it in a bowl, it would just fall through. Whichever way the gravity was pulling it, it would go that way. So maybe that even helps the person who asked this question. Like they were thinking, okay, I've got this contained bowl of dark matter. Can I see it? No, I mean, it would just go straight through it. And I think that person's follow-up question was even, what I'm getting at is, as we talk about dark matter being out there in the universe, but do we quite literally have it all around us more locally too, maybe even passing through us? So Pankaj is right that the density of dark matter is smaller than the density of ordinary matter in the solar system, but there is still lots of dark matter. And yes, it is literally passing through you, me, everyone right now, but just not interacting with us at all. So we don't notice it. Right. Next question, Jenny. What is the latest research on the dark flow and or the great attractor?
Yes, I mean, just to that, from one dark flow to another dark flow. So the dark flow here has nothing to do with dark matter, but the idea is that we have galaxy clusters which have been observed to have a larger than expected velocity in a certain direction. So we have like a bunch of galaxies which are moving collectively in a direction at a speed which we do not expect in our standard cosmology. And this has been around for a while and has been put forward by Alexander Kashlinsky and his team. And people highly debated this dark flow. Some people said this is just an evaluation artifact because other teams used the same data and they said, we do not see this dark flow. We think it's just in a method that they use. But so whether or not this is true, we have a second complementary data set, which has been put forward by Kostas Mikas and his colleagues. And they analyzed galaxy clusters and they kind of like found a similar result based on a totally different approach to evaluate the data. And they see a similar direction, more or less, and a similar speed of these galaxy clusters. And so they say, well, it looks like actually there is some oddity in this dark flow. And so I would say, even though we have like slightly disagreeing directions, we see more or less an anisotropy, like there is a flow in a certain direction and it's not homogeneous and isotropic in that region. So I think there is something to this and it should be followed up and we need more data to look into this. And for the great attractor, I mean, there is no controversy there, but there has been really cool new data from Brent Tully and his colleagues. It's called Cosmic Flows 4, and we have more galaxies, we have more precise data analysis, and I can put the link in the YouTube comments somewhere because they have really great visualizations of all of these flows of the matter density sitting at certain positions and the galaxy flows coming from the so-called dipole repeller flowing through the great attractor. It's really great visualizations, and it has even been like part of music. So Daniel Pomerode has pushed forward that some artists took this over and they're now like kind of like composing music about this, flow, cosmic flows. And it's even been part of Elden Ring, the game, where one of the evil people is more or less looking like the Laniakea supercluster. So it has even made it to popular science, which I think is pretty cool that cosmology even makes it into like mainstream gaming, for instance.
Cool. Please do post a link in the YouTube, but also answer the question in Reddit and put the link there as well. Nico wanted to do a follow-up on this.
My follow-up was, can you please share the link so everyone can see the Laniakea and the flows? Yes,
cool. And then we were going to go to an out there question, quite literally. Are there things out there? So yes, I think this was the first question asked in the AMA as well. I guess I will start with the obvious ones. As scientists, what are your views on extraterrestrial life? Is it a certainty or are we alone in the universe? Is there a more or similarly advanced form of life out there waiting to be discovered? Do you think, given the size of the universe, we would ever be likely to encounter other life? Nico, I think you wanted to go first.
Yeah, thank you very much for asking this question. As I think I already answered on Reddit, first of all, cosmology does not really trying to answer that question, is there life? So our topics are more into how does universe begin, how is evolving, how it's going to end up, what are how much of ingredients and what is the basically universe consisting of, right? Dark matter, dark energy, is there curvature and so on. However, there are branches in proper scientific fields that are dealing with this, and it's a combination of biology and probably exoplanetary or planetary science that are investigating what kind of forms of life could exist in certain conditions, right? Because we know that we humans or bacteria or whatever can exist in certain temperature, under certain pressures, the humidity and so on, right? So then your question should need to be answered first. If you want to answer a question, is there life outside of planet Earth? First, you need to define what life really is, right? Is it some sort of single cell bacteria? Are virus considered life form? Is it crystals? They grow, right? Are they life or not? So I think, and please correct me if I'm right, but I think there was already, we detected some form of life, like bacterial single cell organisms on comets, on surface of Mars or something like that. We already know that there should be something, or at least a protein. I think there was no, Sean, you're nodding. I think there was, in any case. But if your question is intelligent life, so right, there is some sort of civilization out there. So far, we don't have any indication of it. However, the universe is big. Just using probability statistics, probably there is something. Is it intelligent? I can't answer you. And I particularly am not trying to, answer these questions. It is interesting. I think we should all try to answer it. Not us, but people who actually know how to do that. So yeah, I think my colleagues should also try to answer this.
Yeah, my follow-up is more or less just to re-emphasize what Nico said at the beginning, that it's a super interesting question, but we're not the right experts. We're not the experts you're looking for. Yeah, so I think that there is a field who studies this. One of them is called astrobiologists. At Auckland University here in Auckland, there are some astrobiologists. They do some really cool work by going to Rotorua is a city in New Zealand that has a lot of volcanic thermal activity. So some very extreme environments, like extremely hot, like permanently extremely hot, because you've got lots of stuff bubbling up from deep in the Earth's core. And they study how life does and doesn't survive there, with the idea that that's going to be, if there is life on Mars, or was life on Mars and now there's like fossilized evidence of it, that would be the environment it would look like. So yeah, people are doing super interesting stuff in that, but not us, unfortunately. But Jenny did have also a follow-up that you wanted to say.
Yes, I mean, from the theoretical viewpoint, I think maybe the person who asked the question was referring to, there's the famous Drake equation, are we alone in the universe? And so it's just based on like how many planets can we form in our universe and how many of them are actually in a habitable zone so that they can bear life, and so on and so on. And in the end, the question is usually based on all the, huge volume that we have, is the answer 0 or 1? This is more or less usually like debated. Usually it's something in between, like a probability, but some people argue it's more or less we are unique, and other people argue, of course, we are not alone because we have all these possibilities, and so we shouldn't be alone. And I think one of the most interesting projects that I think is currently going on is the Galileo project by Avi Loeb, who says that, well, we have one planet and we can actually have a look whether we already have some signs that some extraterrestrial life form might have landed on this planet. And so I think, why not just have a look at this, and why not just explore it? It's worth the while to dig into this if we want an answer to this question.
I know, I feel like following up on that, I guess it's interesting to look, but not interesting to tell the news agencies of the world that you've found it. So I don't know. I don't know whether the one outweighs the other. Yeah, Robert, you wanted to follow up?
Yeah, also a second follow-up. I just agree with what you said, Sean. So that's I think not what one should do, or maybe claim that fast radio bursts are the sign of extraterrestrial life, which also happened. But no, the point is also right. Even so, I think so. Most people I know, and just statistically, right, you could argue that there should be something out there, right? There should be other planets which are like Earth in all likelihood. The question is then, can you detect them, right? Can you ever see that? Do we basically exist in the right period of time? Because if it's very far away and they exist now, basically, they will only know about us in, I don't know, many million years, and vice versa. So, and given the lifespan of typical civilizations, it's just very, very unlikely that you find each other.
Cool. Pankaj, you have a follow-up on this as well?
Yeah, more about non-intelligent life, but this life in general. We know that James Webb Space Telescope, during one of its first science experiments, detected water vapor in the clouds of one of those extrasolar planets, which is like, one of the perfect conditions for formation of life. So that's something that, a telescope of that magnitude, like, we're adding more and more capabilities to telescopes to be actually able to detect conditions for life in other planets. And so I wouldn't be surprised if, like, just a small amount of time, we might actually be able to have more confirmed evidence of at least bacterial life that Nico was referring to in her first answer to this question.
Awesome. So the next question I wanted to move to is Min, you wanted to have a good answering this. So very kind of modern cosmology question rather than the bigger questions, but this is the sort of thing that might lead to big questions in the future. If one data set says the Hubble parameter, so maybe Min, when you're answering, tell the audience what that is about 72 plus or minus 3.2 kilometers per second per megaparsec, and another data set says it's 73 plus or minus 3.1. Is it possible that combining both data sets yields 68? That is it possible that two data sets prefer a higher value of the parameter, nonetheless prefer a lower value when combined? So maybe use this as an example to fill everyone else in about what the Hubble parameter is, why this is an interesting question. Because obviously, again, the person asking this question knows more than maybe the average person does.
Right.
But then
Yeah,
also
so
answer this person's question at the end.
So the Hubble parameter basically characterizes how fast the universe has been is expanding, and for these questions, it's actually referred to the value of the Hubble parameter at the present time, and the reason that value is interesting is because currently there are different measurements of this value, both using data from the very early one. You use data from the very early universe, which is the CosmicMicrowave Background, and the other using the distant ladder, so measurements of distances. You calibrate at this different scales, and then basically they use CFITs and supernova to get the distance and to infer the value of the Hubble parameter, and then both extrapolated these measurements to redshift 0 to the current time to get the H0 value, which is the Hubble constant. So basically, this is interesting because these extrapolations disagree with each other. If you assume lambda CDM, the current standard model of the universe. So just to answer the questions, I think it's actually a very simple type problem that the person can probably work it out. Like it's just a 1D distribution, right? So assuming that your measurements has Gaussian error, you can assume that the numbers that were given in the questions are just the mean and the standard deviation of these two Gaussians. And then if you further assume that the two measurements are independent, you can just combine these two Gaussians by multiplying them. Or if you take the log, it's just adding the log together. And then you should be able to get the mean and the combined mean and standard deviation, which shouldn't be 68. I would guess. So yeah, I think it's very difficult to try to explain the Hubble tension in that way. So currently we still don't know if it's new physics or systematics, but we're pretty sure that it must be something that we didn't account in our calculations in either of the measurements.
Cool. Nico, you have a follow-up?
Yeah, thank you, Min, for a very nice explanation. I would just only like to maybe say the same thing, but maybe in different words for different audience. This parameter that measures the rate of the expansion of the universe, you can measure it from early times and late times, what we call early cosmology and late cosmology. So basically, you can go back to the CMB that we mentioned, the Cosmic Microwave Background, and infer the number that you pointed out to from that, or you can infer it from what we call late cosmology. It means using something with galaxies, or as Min mentioned, the supernova Cepheids. Cepheids are types of stars. And basically CMB, then you can propagate, or the other thing that if we measure it from now, they should match, but there is a mismatch, and we are trying to figure out why there is that mismatch. And still we are not really sure. So that is the basics of the problem.
Okay, I don't see any more follow-ups on this. So let's go to a new question. Robert, you wanted to have a go at answering this. Does gravity differ in different regions of space for unknown reasons? Is dark matter just gravity doing wacky things out there?
Yeah, very good question. So the quick answer is most likely not. And the reason for that is, so when people discovered dark matter, they of course looked into, maybe we just don't understand gravity that well. Maybe gravity is just stronger than we think, and therefore you can hold together these galaxies, which you couldn't hold together without dark matter. But maybe there's really just the visible matter, and gravity is just very different on these scales, right? So because you always have to keep in mind that you need to keep the gravitational law the same, basically on the scales of where we have tested it, for example, the solar system or on Earth, right? Because if gravity would be much different, we would notice it first here. Of course, you can argue that at different places in the universe, it acts differently, but at some point it gets very, very complicated to write down a variable theory of gravity, which basically satisfies these conditions. And the main issue is that over the past, so since dark matter was discovered by Zwicky and others in the 30s and 40s, since then basically there has been an overwhelming evidence that this dark matter, or this additional matter which does not interact with light, is required in a lot of different systems, like the CMB, like in galaxies, on vastly different scales. And to have a gravity law which can support that, it needs to be very, very wacky. And it's not clear you can write down something like this. And then we go back to what we had in the beginning, that the model gets too complicated. And then you should ask, okay, if I have a simple model like dark matter, simple effective model, right? And we still don't know what it is, but fair enough. A simple effective model, then maybe it is just that.
Cool. I have a follow-up, and I think a few others do as well. I find the discussion of whether the thing that is attributed to dark matter is dark matter or modified gravity in modern cosmology has reached the point where there's no substantive disagreement. It's people think there is, but there isn't. It's just arguing about definitions. The stuff that has been attributed to dark matter can be described by a model called dark matter in certain areas very, 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 very well. The same way that Newtonian physics can describe the solar system very, 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 very well. So I am certain that 100 years from now and 1,000 years from now, dark matter will still be around as a model describing the universe. The same way that Newtonian physics is still around describing the universe. You learn Newtonian physics first, then you learn general relativity and quantum mechanics, which are the more complete things. So whilst it is still possible, and I don't mean this in a like all niche fringe area, I mean it's still possible that dark matter is somehow gravity being modified, but it manifests itself as a field of particles at the kind of areas where dark matter is being tested. It still behaves exactly like the thing that is called dark matter in those areas. It just does. When the cosmic microwave background was being formed, when fast clusters collide, it behaves like dark matter. So dark matter exists, and it might be that there is a more complete modified gravity model that behaves like dark matter and those things. The other thing I wanted to talk about is in the early days, and I guess is what Robert was referring to, that there is there was a kind of a battle between dark matter and a modification of Newtonian dynamics inside a galaxy, and it could be one or it could be the other. Because dark matter is definitely there in things like the cosmic microwave background, I guess the kind of Occam's razor simple solution is that it's also the thing causing the behavior in the galaxies. There are still cosmologists doing research saying, well, maybe it isn't. There are some problems with dark matter inside galaxies. Maybe the thing that is doing the cosmic microwave background is not the thing doing the galaxies. It's not the first time in the history of science that Occam's razor hasn't been satisfied, that the thing that explains one thing somehow doesn't explain the other thing. But yes, it does get more complicated. You have to explain why the dark matter that was there in the cosmic microwave background is not affecting galaxies. So you can do that perhaps by having it being hot dark matter, that it can't cluster inside galaxies. It's still there in the universe now, but it doesn't cluster. So these are extra bells and whistles. So it's less favored than a cold dark matter that is also the thing in the galaxies. But it's worth continuing to explore. So yeah, I think Pankaj, you wanted to follow up, and then Jenny, you as well, and then maybe the next question.
Yeah, I would, as a follow-up, I would like to answer a different but a related question: is how do we know for sure dark matter isn't just a mathematical invention to conveniently adjust our calculations? It kind of reminds me of either, to be honest, asked by Nicole Coase. Yeah, I would say that whenever someone asks me about evidence for dark matter, the one that usually comes to my mind is the bullet cluster of galaxies. It's if you look at that, it's composed of two clusters of galaxies that collided and moved past each other. It's not clear if you look at it only in visible light, but if you look at it in other wavelengths of light, example X-rays, you can see that that they have moved past each other. In fact, as far as visible matter is concerned, the majority of visible matter in this case is gas. And you can see that in X-rays, the gas is at a different location than the stars. And that's because stars, when they collide, the stars, they're just so far away from each other, they just pass right through, whereas the gas doesn't interact, it lags behind. Now you can also see this through the gravitational lens, pun intended, like literally through lensing. And when you do lensing in this region, you find that there are two peaks, and those peaks are very near, possibly coincident with where the stars are, where the visible galaxies are, and not where the gas, which is where the majority of the normal matter is supposed to be, is. So most of the gravitation is far away from where most of the visible matter is, and that is, I guess, a sufficient, like a significant support for the idea that there is a thing called dark matter, and it is actually is in much more abundance than normal matter.
Yeah, Jenny, I think you wanted to follow up as well.
Yes, just brief follow-up. I mean, from the history of science, I think it's quite interesting to see that first we have these discrepancy of missing masses on galaxy scale or galaxy cluster scales. But on the other hand, we had this missing mass in the cosmic microwave background, which came from more or less a different perspective. And I think the case for dark matter was made when people realized that actually two of these first separated phenomena can actually be explained with the same stuff. We just add this one ingredient, just one dark matter, and then we can explain all of them in a kind of unified way. I think this is one point that I see is quite interesting and speaking in favor of dark matter. And for the other side, I mean, Sean also said it's worth pursuing modified gravity. And I'm also on that side because I think in the end, our observations should be explained, I mean, in a consistent way. And so this pursuing modified gravity gives us a different viewpoint. It sees, can we actually fine-tune gravity, and on which scales does it work or does it not work? Because people will always ask, not only we have one solution that works, but could it not be in another way? And so I think these modified gravity theories, which currently do not have a general relativity equivalent, still needs to be pursued further in order to see, is there a second solution? Could we explain it in a different way? And does this give us new input how to explain all the other observations as well?
Okay, I don't see any follow-ups at the moment. So the next question was going to be, do you think we will know what dark matter and dark energy are anytime soon? Nico, you wanted to have a go at that?
Yeah, sure. First of all, we already know actually some things about, actually many things about dark matter. We don't necessarily know the nature. However, we know something that's very important, which is the equation of state. So I would, if you're not familiar with the equation of state, maybe you can just look it up online. But basically, that is also one way to distinguish between dark matter and dark energy. Usually when they say what's the difference, well, you can, in physics terms, you can very easily say they have a different equation of state, so they will behave in a different way. So in order to understand the nature and anything that we would like to investigate, we are now in the state of, we are building a lot of experiments and building a lot of detectors, and like biting away around the edges to get to the center. But to say that we don't know is actually not true. We do have very clear ideas, and a lot of people are working very hard on understanding the nature of dark matter and dark energy, being that from a theoretical point of view, like Jenny, right, observationally, data analysis, and so on. So I would like to also ask my colleagues here if you would like to follow up on that.
Yeah, I kind of want to follow up a little bit on you, and I realized I wanted to follow up on what Jenny was saying. I mean, it's one of these, like, just emphasizing and agreeing with what Jenny said about, we only need the kind of one number to describe dark matter. It's easy when you're outside of cosmology to be thinking like, oh, they've just invented this dark matter thing, and it, you know, you can tweak it and just get it to do whatever you want it to do. That's not true. It's one number. You can parameterize that one number in different ways, but one way is the density today of dark matter. And that's all the freedom we have. And it's cold dark matter, so it doesn't do other stuff. Like, it's just that. And that is enough to more or less explain everything. It does have these regions where it gets a little bit fiddly, but those regions are also where there's lots of confusing explosions of supernovae and centers of galaxies going on, where it's very, very clear in things like the cosmic microwave background. You've got that one number, and it does manage to be very predictive and to explain these things. So yeah, from the outside it might look all kind of made up, but from the inside it's one number. There's not that much freedom. The other thing I kind of wanted to I guess also emphasize what Nico was saying on the dark matter, dark energy divide. These things are two very different things, not just in their phenomena, but in like how well we understand them, I guess. Like, the problem with dark matter and trying to work out what it is that we've got lots and lots and lots of very good, very compelling models, and we don't know which one is true, if any, but we don't know which one is true. The problem with dark energy is that we don't have any compelling models. There's maybe one, which is part of general relativity, a thing called a cosmological constant, but its value then is just utterly baffling. It's a very, 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 very small value then compared to what one might naively expect. But I am yet to see, other than a cosmological constant, any dark energy model that feels even remotely compelling to me. And yet on the dark matter side, there are probably thousands that are like, okay, yeah, if that turned out to be the dark matter, I'd be like, yeah, all right, that makes sense. So yeah, very different problems. We don't know which one that will turn out to be the correct dark matter one, and no one really has much of a grasp on dark energy. Min, you wanted to do a follow-up?
Yes, just very briefly about what you said about dark matter. I think we as a community agree about the existence of dark matter, and we are now at the point of characterizing the components of the dark matter, because we know on large scale, like the bulk of the dark matter should behave like cold dark matter. It shouldn't move very fast, relativistically, for example. But we now are at the point where we also try to quantify if there is any of like the ultralight dark matter, for example, how much of the what is their fraction in the total dark matter. So
cool. Actually, I just wanted to clarify two things I've said might sound like they're clashing. One was that we've only got this one number, and the other thing was, you know, you've got ultralight dark matter, you've got hot dark matter. These are adding in new numbers that could add in new phenomena, but none of this new phenomena has actually been detected. It's just like, okay, if dark matter is this, what interesting new things could it have? Let's go look for those new things. The stuff that is actually measured is all just due to this one number. Right. The next one, I think, for Jenny wants to answer it, is, will we ever develop technology to see past the CMB? What would such technology look like?
Well, I mean, actually, we are already more or less indirectly seeing past the CMB, because we have a notion how our first how our first nuclei formed in the primordial nucleosynthesis. So we actually see beyond beyond the CMB, because these nuclei have formed beforehand. And there will be some neutrino background, which will be detected in future experiments. And of course, we are all waiting for the gravitational wave background, which might us even give some hints whether inflation happened and how it did. And so I think the next decade or even 20, 30 years will be very exciting in that respect, and we will probe beyond the cosmic microwave background.
Yeah, I guess we might not be present super experts on this, but maybe we can have a good go. There was this stochastic gravitational wave detection 2 weeks ago by the nanograv and European pulsar timing array, and I think a few other pulsar timing arrays. So what this was detecting is a stochastic gravitational wave background. So it wasn't detecting gravitational waves from individual isolated events, the way that you might have heard about gravitational waves a few years ago, this LIGO Virgo on Earth detectors that have been detecting individual black hole collisions. So the pulsar timing array is the idea is that you've got all of these pulsars out in the universe, and they rotate with a very, very precise period. But if a gravitational wave is traveling through them, you get little changes in the period. And if you've got a whole array of pulsars put there by nature, obviously we can't go out and place pulsars, you can kind of detect that there are gravitational waves coming through them. Conceivably, if there are enough gravitational waves being produced in the early universe, something like that would be able to see, or hear perhaps is a better word, although still not perfect, these earlier gravitational waves that Jenny was talking about. But yeah, other than gravitational waves and indirect stuff like the abundance of nuclei, you certainly can't see with a telescope beyond the cosmic microwave background, because the universe becomes opaque, just like I can't see through the wall behind the camera. Right. Robert, you might have a question based on a follow-up based on a previous question. So the dark matter, dark energy question. Do you want to to jump in on that?
Yeah, I mean, there was also the question when dark energy and dark matter was produced, if it was produced during the Big Bang, before. So yeah, we don't know. But since there are a lot of dark matter models out there, as we discussed now, a lot of times, right? Those are produced during different times, but all after the Big Bang, right? Because as we discussed as well, we cannot look before the Big Bang, so we don't know what this is. So unless you have some model with a cyclic universe or something like that, then this might be possible that you get evidence from there. But in the end, physics is driven by data. And if we don't have any information, we can't say anything, right? Because physics is the science of measuring things, basically. So there exist dark matter models which were produced during inflation, just before inflation, or after inflation. There are different kinds of models, but they are produced the dark matter particles, or the dark matter as we see it today, as these collisionless particles, are produced early in the universe, because they have to be there for the CMB to enable the structure growth, basically, we see today. For dark energy, this is a bit different. So dark energy, I will just jump on the train Sean started, that the most compelling theory we have is the cosmological constant. And the cosmological constant is a property of space-time, and it is in the equations of general relativity, and it is just always there. And the only thing is that in the universe, it was not important in early times relatively to the other components of the universe, but it was always there. And it always basically drove the accelerated expansion of the universe. But since the other components, for example, matter and radiation, which add attractive on the gravity part, were much more important in early times, there was no basically repulsive part of gravity, so there was no accelerated expansion, but the cosmological constant was always there. Yeah.
Cool. Nobody appeared to have a follow-up to that, so cool. Robert has covered every base that any of us wanted to cover. Excellent. No, Jenny has a follow-up.
Yes, I mean, we could say we were happily living in a world without any cosmological constant at all until we finally saw the supernovae, and we couldn't explain it anymore with just the matter-dominated universe. I mean, this was worth Nobel Prize to see that the universe is actually acceleratingly expanding. And that this was, I would say, one of the biggest revolutions in cosmology that we had in recent times, that we saw we need to include this cosmological constant, at least this one, in order to explain our observations. And I mean, Einstein formally said it's just his biggest blunder. Then he inserted it to obtain like a steady state cosmology, a static universe. Then this was refuted by quasar observations. And then we thought, okay, now we're living in a matter-dominated universe. And then came the supernovae, again, introducing this cosmological constant as a necessary ingredient to explain our data. And I think this is quite an interesting evolution, how like the cosmological constant entered into the equations, was abandoned and came back again. And today, I think we even have more observations which hint that we need at least a cosmological constant to explain, for instance, like other observations in the late universe as well. So,
excellent. Robert has a follow-up to the follow-up.
Yes, I just wanted to add, right? So I think, so if we discuss it today again, right? So maybe in the 90s, people were happy with no cosmological constant, but I think today people would say, maybe why is it then zero, right? Because it is there in the equations, and zero is a very particular value. Could be just that, right? But people are asking now, okay, why is the cosmological constant so small? Because if you do calculations which are based on quantum theory, and to calculate the vacuum energy, you expect something which is much, much larger by many orders of magnitudes, which has been called the worst prediction of theoretical physics many times, I think. And the question is then, okay, if this vacuum energy exists, because it should be there in principle, why does on large scales where the cosmological constant is important, does this kind of cancellation happen? It could be because we don't have a theory of quantum gravity, but in general, why is this cancellation happening so that the observed cosmological constant is so small? Because if it would be so big as predicted by quantum theory, we wouldn't be here. So, yeah.
Yeah, that dark energy is definitely a mystery. Okay, we'll have one last proper question, and then we'll maybe close up, hopefully with a kind of nice closing up question. We're kind of brainstorming behind the scenes to think of one. If you want to ask one in the YouTube chat, here's your chance. So the last proper question: spatial distribution of matter in the universe is homogeneous and isotropic when viewed on a large enough scale. This never made sense to me. If someone could explain it to me in layman's terms, I would appreciate it. What is the point of ignoring the obvious differences between empty space, voids, stars, galaxies, clusters, superclusters, filaments? Nico, you want to have a go at that one?
Absolutely. So first, let's just quickly define what this homogeneity and isotropy means. So that means homogeneity, that universe, each chunk is looks more or less the same, or has the same amount of stuff in it. And isotropy means in every direction, wherever you look. And that thing holds, it's called a cosmological principle, and it holds on larger scales. So it means when you zoom out, if you would look at the universe from the outside, I'm using the term very loosely, on large scales. However, as you say, we definitely have some structures in it. So it's like honeycomb structures, right? There is a larger void. So that means places with much less stuff in it, fewer galaxies and so on, filaments and so on. Or if you probe more inside or zoom in, then you would see galaxies and then eventually stars and planets. We care about all of that. However, depending on your field of study, if you're studying cosmology, for example, something that's called like large-scale structure cosmology, then you would look at this big chunk of universe zoomed out. And then astrophysicists are people who are looking into galaxies, stars, and so on. So we are absolutely not including those things. Also in cosmology, there are people who are actively working on voids and using very smart statistical techniques to infer a lot of information using these structures that are called voids. So everything is being used in science to infer some knowledge out of it. It just depends on if you work as a cosmologist, if you work as a void cosmologist, if you work as an astrophysicist, and so on. Even
Min,
though voids. Yeah.
Oh, sorry. Min, do you want to go next?
No. Yeah, maybe Min, yeah.
Oh, yeah, sure. Yeah, so I will just echo on what Nico said, but maybe a bit more technical. I think that's the theme for this discussion, Nico and I. But yeah, so what we mean by homogeneous or isotropy is usually in the statistical sense. So we don't mean that if you so all the structures are the same and you ignore the large scale structures of the universe, we actually use that information to infer or to constrain our model, right? But what we usually mean is that when you measure or you observe a certain volume in the universe and you see these large scale structures and you measure some certain statistics from them, like how strong they cluster together, and if you go to like another region of the universe and you measure for the same, you observe a same volume, you would, and then measure the same statistical quantities, you would your statistical quantities should agree. So that's what we usually mean by homogeneous.
Cool. Jenny, do you want to have a follow-up?
Yes, I mean, I would say, I would explain it from a different viewpoint. I would say, what can we measure? The only thing we can measure is change. And so if we want to take a look at our observables, it's pretty easy in order for us to measure something, to say we have something homogeneous and isotropic as a background, and we measure the changes on top of this. And so if we do this for the entire universe, then of course, at the early times, we have more or less an isotropic and homogeneous cosmic microwave background with just tiny fluctuations. And there it's pretty easy to have homogeneity and isotropy. But if we go to late times, we enter the nonlinear regime and structures grow nonlinearly. So we enter the regime where we have galaxies, clusters, and all of this, and voids. And so in the end, at late times, it's much harder to kind of like find this homogeneous isotropic background. And this is why it looks odd to us in the late universe that we would have homogeneous isotropic background cosmology. But it just means that we have something behind our observations to measure the change, to measure these galaxies and clusters on top of this homogeneous isotropic background.
Okay. We've still been brainstorming of a nice question to end with, because we started with what we're looking forward to. So we've decided we're going to, and we're putting ourselves on the spot here. At the beginning, we said, what are we looking forward to? So now we're going to, at the end, say, what have we found the most interesting or most notable, whatever we just feel like talking about from, let's say, the last 10 or 20 years of cosmology. Do I have anyone volunteering to go first? Because I haven't even thought about it. Well, yeah, Nico, you can go first while the rest of us think.
Yeah, maybe it's an ambiguous question, but bear with. So I think in the last 20 years, we have seen a rise in the number of collaborations, like physics, in field of physics. I'm not saying that we did not have collaborations before that, but now that the science is growing together with the technology and of course the internet and all of the cool stuff that we have now. So it's making our lives easier and making it possible to do science more easily, accurately, and precisely. Therefore, there's also, so by collaboration, I mean people from all over the world come together and make up a plan, get the money, and build a detector or a telescope and use the data, and all of it together work on understanding the universe or whatever the goal is of the experiment. So in that sort of sense, just shows that the more collaborations we have, the better outcome and the more understanding of the universe we're going to have always. Because science is usually, you need to have a collaborative effort at this point in time. I'm not saying that individuals can't do it, of course they can, but it's always easier when there's more people coming together and they're doing the work. Of course, in the last 20 years, I mean, we discovered, not we, but we as a society discovered Higgs. And I think that was really fantastic. And then we had gravitational wave detection. It's not directly cosmology, but it's definitely connected to universe. So I think that is an outstanding breakthrough that we had in the last 20 years.
Cool.
And
Sorry.
Sorry. So we had a very image of a black hole, which is also absolutely mind-blowing.
Awesome. Sorry for jumping in there. Jenny, do you want to go next?
Yes, I mean, I can immediately connect to this because I was pretty much intrigued by gravitational wave detection in 2017. Because, I mean, this is, I think, for me, one of the first times where we actually can constrain our noise so well, and our theory is so sophisticated that we can build a matched filter to get a signal out of a huge amount of noise from an experiment which has been like fine-tuned by a lot of people over like 30 years or something like this. And for me, this was really impressive that we are at this level, that we can actually detect such tiny signals.
Awesome. Pankaj, you want to go next?
Sure, yeah. So I'm like, new to the field, so most of this is based on textbook stuff. But as I say, the last couple of decades have really been precision cosmology, as they said, because we've just had so much more data. Example, the WMAP CMB experiment and the Planck measurement is one of my favorites. And then just the advent of more computing power so that we can use methods that I learned in school, like Bayesian analysis and like, match filtering that Ginny talked about. And like I learned Bayesian analysis in like a completely different context. Like I learned about like, how do you figure out like, what is the probability of a coin given like, you observe certain heads and tails, and for that to be then used in like, gravitational waves and like everywhere in cosmology. Like I just, at some point I read in a paper that started with like Bayesian analysis, like it's the bread and butter of astronomy these days. And so I think I can like very much agree with that. And I very much love the direction that we're heading, given the data and the computation power and just more Bayesian all the way.
Yeah, next, Robert.
Yes, I will go back a bit further even and just say in general, the detection of the cosmic microwave background. So one thing, what I like about cosmology is that it connects so many different fields of physics. And what we haven't talked about that much in these 90 minutes, basically the production of elements in the early universe. And so you can, for example, ask the question, if you take all the stars in the universe, can they produce the element abundance we see today of the light elements, for example, helium? And the answer is no. They don't have enough time to produce it. So they have to be, when the universe was smaller earlier on, it was also hotter, the hot Big Bang, so the temperatures were high enough to produce light elements. And then in order to produce these light elements, you know that there will be some radiation field associated to this, because there have to be the photons that you can, which are released basically when you produce these light elements. And how the universe expands during this very early times, during the first 5 minutes of its evolution, is very, very crucial. It's, for example, crucial how long the lifetime of a neutron is, and that it decays into protons. And we can constrain basically with this the abundance of elements we see today. And when we look at these elements, it matches. And you can then see the cosmic microwave background, which was found in '65. And I think this is just impressive, because it was predicted much before that. And yeah, that is just really amazing to me.
Cool. Min, and then I'll have to put myself on the spot. Still not sure what I'm going to say.
Yeah. So so I think it's just a bit summary of everybody already said. I think what is exciting is that we now getting a view of the universe at so many different wavelengths, at so many different scales, right? And and also like the statistical power of the data is getting to the point. I don't know if it's exciting or concerning or irritating. It depends on whom you are talking to. But now we have to worry about systematics, and I think even though the space for the theoretical models are still like a lot, there's still a lot of freedom. I think in a few years or 10 years, that would not be true anymore. We would be, because whatever model you have to fit the observations at different scales and different wavelengths. So yeah, so I think that is the exciting part.
Okay, I'm now on the spot. I am going to cheat blatantly and increase the 20 years to 300 or 400, and just say that basically, I don't think that we in the modern world like fully appreciate how much of a just absolute sledgehammer shattering of glass, catastrophe breaking change in our collective consciousness, the kind of Copernicus Galileo stuff really was, to go from thinking you're the center of the universe to not the center of the universe. And then every step after that has just been like, yeah, we're even more not the center of the universe. But I think in terms of, there've been lots of technological breakthroughs, inventing of lenses to have telescopes and this sort of thing, that have triggered kind of consciousness changes. But in terms of theoretical changes, stuff like maybe quantum mechanics is the next closest, maybe even bigger, but just going from the center of the universe to just irrelevant almost in the universe. We kind of grow up knowing that we're just a planet in a solar system. It's just a solar system in a galaxy, and it's just a galaxy in a cluster of galaxies, and that everything along that is not special. But before these guys kind of realized that, it's it's a very different perspective. Yeah, Jenny just wrote a comment in the chat that I think I should share, that historically cosmology has been notorious for only being correct to an order of magnitude. As Pankaj said, we're now in the precision era, so this is no longer true. But yes, I was correct with an order of magnitude. 30 years is 300 years. So 30 years ago, that would have been acceptable as a cosmologist, but nowadays, no, within an order of magnitude is no longer acceptable. So I did cheat. But on that note, I think we're finished. We've gone over the 90 minutes we initially scheduled. But thank you, those of you who've been watching. Thank you, those of you who watch it in the future. Thank you, Min, Jenny, Nico, Pankaj, Robert, for joining us now. And if you have any further questions, feel free to jump on the Reddit AMA and ask them, and hopefully we'll find time to answer them over the next couple of days.